Good morning everyone. So here is my first lecture based on introduction to signal and system. So in this lecture we are going to see what are signals and what are systems, classifications of signals, how signals will respond to a particular system and what is the output response of that particular system. So in this lecture firstly we start with the fundamentals of signals and systems. So signals, as you can have, that is a very small thing that will convey information on the nature of a physical phenomena. So you can say that it is a kind of a function of one or more variables that convey information on the nature of any physical phenomena. For example, here there are some examples written over here. That is, first one is the voltage with respect to time, second is the current with respect to time, and similarly we can define a signal, that is x of t. So here are two categories of signals, like one is one-dimensional signal and another is two-dimensional signal. So this t, small t here, is known as independent variable. So a signal is a function of one or more independent variables. So if it is defined for one independent variable, then it is called as one-dimensional signal. And if it is defined for more than one independent variable, so that is called as multi-dimensional signal. So functions which depends on one or two or more than two independent variables or variables, that is, for example, image. So that is dependent on more than two independent variables. So that image is called as a multi-dimensional signal. So here we can also define a system. So system is basically an entity or operator that manipulates one or more signals to accomplish a function, thereby yielding a new signal. So here we have an input signal. Suppose the input signal is xt, the output signal is yt, and there is a system which is having an impulse response ht. So this ht is defined as impulse response. So whenever we give any input to a particular system, it will give you some response. So if it is a kind of some impulse type of signal, which we will discuss later on, so it will called as impulse response. So commonly encountered systems are communication systems, automatic speaker recognition system, aircraft landing systems. So now we will discuss about classification of signals. So in the classification of signals, we have two types. First one is the continuous time signals and the second one is the discrete time signals. You can see from the first figure that it is a continuum of taking all the values of the time period. So here the amplitudes vary and it is taking all the values of the time period. There is every value from integer to fractional and all. In the second part, we can see here easily that it will take only some specified values. So these specified values are basically integer values. So suppose here the integer values is 1, 2 in the x-axis, 1, 2, 3, 4 and so on. And similarly in the negative side it is -1, -2 and so on. So the amplitudes are defined only for the integer values here in the case of the discrete time signals. So for many cases, xn is obtained by sampling xt. There is a process which is called as sampling. So we can sample a continuous time signal to obtain our discrete time signal with this formula, that is xn is equivalent to x of nt, where n equivalent to 0, plus minus 1, plus minus 2. According to the requirement, what we want the samples at 0th position, at first position, second position, or similarly from -1, -2 and so on. So are there any requirement for the sampling? Obviously yes. There is requirement for the sampling to obtain our discrete time signals, and these discrete time signals are basically mainly used in audio systems nowadays or digital pilots and so on. So now we have another category, that is even and odd signal. So by definition, this is a second category of the signal, classification of signal. So for the discrete, for the continuous time signal, it is x of minus t, that is equivalent to x of t. This x of minus t is basically the reversal of xt. This is reversal of x of t about t equivalent to 0. About the origin, you can say. And similarly, x of minus n is equivalent to x of n. So if these type of signals happen, then these are called as even signal. Similarly, for odd signals, we have x of minus t is equivalent to minus of x of t. So here there is a reversal, or you can write like this, x of t is equivalent to minus of x of minus t. So there is a reversal around the y-axis. Also, there is a reversal around the x-axis. We have to flip firstly around the y-axis and then flip around the x-axis. Then we can obtain this type of signal. So, these type of signals are called as odd signals. So, we have x of minus t is equivalent to x of t. For example, if we draw this type of signal, x of t 0, minus 1, 1, we can easily get x of minus t for this, and which is similar to this, because when you have this type of particular thing to have a reversal around the y-axis, you will obtain the similar type of signal, that is from minus 1, 0 and 1, that is x of minus t. So, these type of signals are called as even signals. Similarly, for odd signals, we can have this type of representation. So, this is a signal xt and x of, and it is crossing the 0th position, and it is minus 2, 2, 1, and similarly minus 1. And when you flip the signal, it will give you the same signal when you flip firstly around this axis, or you can say in the same way, that is flip like this and then like this. Okay, and then we have to this is x of minus t. So, you can see x of minus t is not equivalent to x of t. So, in this case, again we have to flip the same signal around the x-axis. When you flip the signal around the x-axis, you will get the same result, which is shown in the above xt. So, this type of signals are called as odd signal. So, for the even signal, we have to see x of minus t is equivalent to xt, or x of minus n is equivalent to xn. For odd signal, we have to see x of minus t is equivalent to minus of xt, or x of minus n is equivalent to minus of xn. So, any signal can be compressed of the combination of these two, even and odd part. So, we can represent xt as x of even t plus x of odd t. Similarly, x of minus t is equivalent to x of et minus x of ot, or we can have x of even t, x of odd t, like x of t plus x of minus t divided by 2, or x of t minus x of minus t divided by 2. These two formulas are for getting the component of even and odd. Next is the periodic and non-periodic signal. So, any continuous time signal is called as periodic signal if xt is equivalent to xt plus capital T, where capital T is the fundamental period of the signal, and this T is defined as the fundamental frequency in terms of like f naught equivalent to 1 upon T naught, and T naught is the smallest possible value of the capital T. Similarly, for discrete time signal, it is xn is equivalent to xn plus capital N, and here the capital N will be the fundamental period, and this N will be calculated with the help of f, which is equivalent to k by N. So, if we get the value of omega naught firstly, then we will take the value of f, and from there we have the numerator upon denominator that is equivalent to k by N, and we will easily obtain our fundamental period of the discrete time signals. Next is the deterministic and random signals. So, these deterministic signals are those signals which have no uncertainty and which can be easily expressed with a particular expression. On the other hand, a random signal which is uncertain before it occurs, for example, thermal noise, and you cannot specify this particular random signal in the form of the mathematical expression. So, those signals which can be represented in the form of mathematical expressions are called as deterministic signals. So, here we have mathematical expressions. And in the case of the random signals, we cannot have mathematical expressions. Next is the energy and power signal. So, every signal must contain some energy or some power. So, if the energy of the signal is finite, in that case the power is 0. Similarly, the second class of the signals are, if the power is finite, then the energy is infinite. And the third class is neither energy nor power is defined for a particular signal. So, in the continuous time signal, we have energy formula which is given by mod of xt ka square integration over minus infinity to infinity dt. So we can write energy as minus infinity to infinity. You can also write like this or like this, mod of x t square and dt. So by this we can calculate the energy of a particular signal. In this case, if the energy is finite, then average power is 0. This is the first classification. Similarly, power will be defined by energy by time. So we can write limit t tends to infinity 1 upon 2t minus t to t mod of x t square dt, which we can you write like x square t dt. And in this case, when energy is finite, we have average power is 0. Similarly, for discrete time signals, we have energy is equivalent to minus infinity to infinity x square n. Similarly, power is defined as limit n tends to infinity 1 upon 2n plus 1 summation over n equivalent to n minus n to n x square n. So here there are 2n total. Total number of terms from minus n to n is 2n plus 1. Similarly, we have the power here limit n tends to infinity 1 upon 2n plus 1, same as in the case of the continuous time signal. So energy signal is, if energy lies between 0 to infinite, then it is called as energy signal, or we can say that energy is finite. Similarly, for power signal, when it is lie between 0 to infinite, then it is called as power signal. Now next we have analog signal and digital signal. Various kind of signals are there. So next category is analog and digital. Digital is another part of the discrete time signal. In the digital signal, we have binary representation, that is 0 and 1. So you can see from the first figure, that is a continuous time signal, which is a random signal. The second figure shows the discrete version of that continuous time signal. Third signal shows the continuous time discrete valued signal, which is a step type of signal. And the fourth type is the binary representation of the discrete valued signal. So there are basic operations on signals. First operation is amplitude scaling. So if there is a signal which has a some amplitude, suppose A, and if it is multiplied with C, it will be expanded, or you can amplify it with C factor. So C is basically a gain, or if C is greater than 1 and C is less than 1, then it is called as attenuation. Similarly, addition between the two signals, yt is equivalent to x1t plus x2t. Similarly, in discrete time, x1n plus x2n. Multiplication, it's a simple multiplication, x1t plus x2 multiplied by x2t. And similarly, yn is equivalent to x1n multiplied by x2n. Differentiation, again, yt is equivalent to d by dt of xt. And in this case, discrete time, it is a difference equation. So we do not consider here the differentiation. Similarly, the integration from minus infinity to t x tau d tau. In this case, we do not consider the integration. Time scaling, I have two parts. First one is the compression and the second one is the expansion. So if value of a is greater than 1, in the case of yt is equivalent to x of at, suppose a is equivalent to 2. In that case, the time scale will be compressed or divided by 2. Similarly, if a is less than 1, suppose a is equivalent to 0.5, then in that case, the time scale will be expanded by 2. Similarly, in the case of the discrete time signal, so reflection, or we can say have time reversal, which we have earlier discussed in the even and odd signal, yt is equivalent to x of minus t, or yn is equivalent to x of minus n. Shifting, it can be of two types, that is delayed or advanced. If t naught is positive, then it is called delayed. If t naught is negative, then it is called advanced. That means xt plus t naught, and the signal will move to the left side. If it is delayed, it will be moved to the right side. Similarly, for the discrete time signal, combination of all these, that like for example, yt is equivalent to x of at minus t naught. In this case, we first follow shifting and then scaling and then reversal. So firstly, you follow shifting by a factor t naught, suppose at minus t naught, at minus 2, suppose, so 2 is the, like for example, x 2t minus 3. So firstly, we have to see the shifting of which is a particularly delayed signal by 3, and then scaling by a factor of 2, which is a compression, and then we have a reversal we can also have in this question, but here it is only two things, that is shifting and scaling. So rules for shifting, here we have already discussed that yt is equivalent to x 2t plus 3. Similarly, we have to firstly advance the signal by 3 and then compress the signal by 2. So elementary signals are there. some elementary signals which is exponential signals. So it is defined as b of e to the power at, or you can have e to the power at or a to the power n. It can also be written as e to the power at or a to the power n. So we have a factor of a less than 0, then it will be a decaying, a greater than 0, then it will be a growing. Similarly, n greater than 1, it will be growing, n lies between 0 and 1, it will be a decaying, or n equivalent to 1, it will be a DC signal. Sinusoidal signal can be defined as a cos omega naught t plus phi or a cos omega naught n plus phi. Similarly, for the discrete time signals. Unit step, now we have a basic or elementary signal that is called as unit step function, which is very important function in further units. So ut is defined as 1 for t greater than 0 and for t less than 0 it is 0. Similarly, for discrete time it is defined as un is equivalent to 1 for n greater than equivalent to 0 and t n less than equivalent to 0 it is 0. So for t, if you can define ut like this, it is always constant from 0 to 1, and similarly for discrete time it is having the value, at every value it has a value of 1. This is un versus n, and because it is for discrete time 0, 1, 2, 3, 4, 5, and this is for continuous time, it is of like this. Unit impulse function, which is represented by del t, and del t is equivalent to 1 for n equivalent to 0, t equivalent to 0, and 0 for otherwise, or we can have a relation property that is minus infinity to infinity, del t dt is equivalent to 1 for t equivalent to 0. Similarly, for discrete time, we have del n equivalent to 1 for n equivalent to 0 and 0 for everywhere. Similarly, for unit ramp function, we have rt is equivalent to t for t greater than equivalent to 0, and for t less than 0, it is 0. RT is equivalent to, RT can also be defined as T of UT, or UT can also be defined as d by dt of RT, which you can easily solve with a relationship that will give you 1. Similarly, Rn is equivalent to n for n greater than equivalent to 0 and n less than 0. For n less than 0, it is 0. Now we will come to system properties. So we have some system properties. We have already discussed that what is system. Whenever any input is given to a particular system, it will give you some response. So yt is a response to a particular system which is having an input xt, or we can say yn is a response to a particular system which is having an input xn. So now h is the notation which is given to a system which is particularly a transfer function, or in the time domain it is called as a impulse response. So firstly it is stability. So in the stability we used to read that is BIBO, which is called bounded input and bounded output stability. So whenever we give a bounded input signal, it will always produce a bounded output signal. So if this happens, then the system is called as a stable system. Second is the memory or memoryless. Memory or memoryless means static system, which is dependent on the present value only, not on the future and the past values. Similarly, with memory means it will depending on the present as well as in the past values. So it is called as with memory system. So here are some examples written below, that is yt is equivalent to 5 of xt plus integration over minus infinity to t. Whenever there is integration or something, then obviously it has some memory or some past values. Similarly, yn is equivalent to summation over m equivalent to n minus 5 to n plus 5 xm. It is also a memory system. Memoryless, we have yn is equivalent to xn plus x square n. When you put n equivalent to 0, it will give you y of 0 is equivalent to x of 0 plus x square of 0. It will only give you the values at the same instant, that is at t equivalent to 0 or at the present instant. So you are taking the value at t equivalent to 0, and also the inputs are defined at t equivalent to 0. That is the same instant. That's why it is called as memoryless system or static system. Memory with memory systems are also known as dynamic systems. Third category is causal and non-causal. Causal systems are those systems which depends on the present as well as the past and the future values also. And the non-causal, present and the past values, sorry, not on the future. And the non-causal systems are those which depends on the present output, also on the future values of the input. So in the non-causal case, with the present we have some future values. In the causal case, with the present we have the past values also. So a memoryless system can be a causal system, but a causal system cannot be necessarily a memoryless system, because in the causal system we have the present and the past values also. In the memoryless system we have only the present value. So the memoryless system is called a causal system, but not a vice versa. Time invariant system is when you provide a delay of something, suppose tau or t naught to a particular input, then it will produce the same output, that is yt minus t naught. So here there is a relation, xt minus t naught will be given to a system and it will be producing yt minus t naught. Similarly, xn minus n naught is given to a system, it is producing yn minus n naught. So that means the system is time invariant. If it is not happening, then the system is called as time variant. Linearity is composed of two things, that is superposition and homogeneity. So superposition is the sum of the two signals, that is x1t plus x2t, and the homogeneity is particularly the scaling factor, that is a1 or a or b, something like that. So if x1 is given to a signal system, then it is providing you y1t. If x2 is given to a system, it is providing you y2t. If so on, a1 x1t plus b x2t is given to the system, it will providing you a y1t plus b y2t. So this system is called as linear system. Else, if it is not happening, then it is called as non-linear system. Similarly, time variant and invariant system. So already we have discussed that time invariant systems are those in which we are providing a delay of t naught, and it will also provide a output with a delay of t naught. Then it is called as time invariant. Otherwise, the system is called as time variant system, which is shown here also in the same way. That is, when the delayed output of the system is equal to the output due to the delayed input for all the possible values of t, then the system is called a time invariant system. For example, yt is equivalent to 2t square xt. Similarly, if yt is equivalent to, suppose, x of t or t plus 2 plus x of 2 minus t, like this. So this system is time variant system, because when you change the shift the input, it is having a shift in the t naught, but if you shift the output, it will produce some another output. So in that case, both the things are not equal. For this example, it is not equal, xt minus t naught is not equivalent to yt minus t naught, and in this case the system is called as time variant system.